Firstly, the background and purpose of the research are described. ICN CCN use string-based identifiers instead of IP address, which are a set of predefined numbers used in the existing Internet architecture, the IP architecture. In particular, the software implementation of CCN defines a hierarchical identifier named content name. The advantage of content name and hierarchical character string identifiers are that there is no limit on the number of addresses when compared with IP address, and that the content is easy to understand when people see the address directory. In addition, a common advantage with IP is the ability to aggregate. While the demerit of the routing table becoming broadened when registering content names, which are character strings in the routing table, content name with the same prefix and forwarding destination can be aggregated and registered in the routing table by hierarchization. One of the advantages of hierarchical names is that they are easier for humans to understand, but the total length is expected to be longer in order to unequally identify the content. On the other hand, since the individual elements in the hierarchical names are considered to be independent, we think that it may be possible to obtain the content name by using some of them. If content retrieval and search by some elements of the content name can be performed, uh, consumers who are not network administrators will be able to collect content directly without going through the current search engines such as Google. Next, regarding the proposed method. First, let's take a look at the overall flow. The system user inputs some keywords and search terms, and the system generates multiple content names based on the search terms and sends them all as interested packet. There are various ways to generate content name, but the easiest is to generate a hierarchical name by reordering such terms. Of course, if the system relies solely on such terms from the system users for input, it's unlikely to be able to construct a practical system, as it is unlikely that identifiers associated with real contents will be found. Therefore, we consider collecting and using information on content name from prefix of content name registered in FIBs that are known to exist in order to retrieve content. There are two main inputs required for the proposed method. There are two sets of words of content name which is already known on ICN CCN networks, and a set of such terms entered by the system user. The two are combined to create a content name that can retrieve the content. The reason why a non-content name is needed is this, that a hint is needed to generate a new candidate content name. By doing so, we can reduce the number of generated content names and the number of sent out interest packets, while increasing the possibility of getting the content that users want. Now let's move on to the actual generation algorithm. The produce is divided into three major stages. First, select a location that can be inserted into an existing content name. Next, choose the insert point. Last, insert the search term into the selected insertion location. If the number of elements of the word set included in the arbitrary content name used for the generation is k, and the number of elements of the difference set between c and u is n, the number of content names generated by this algorithm is represented by the formula shown in the slide. Increasing the number of existing content names used during generation will increase the number of content names generated. But as in this study, we are considering using Jackal conscience and other factors to adapt content names that are similar to the user's search word set. In order to equal the performance of the proposed method, we conducted evaluation experiments. In this presentation, we implement the proposed algorithm under limited conditions. This time, we implement it under two main conditions. First is the set of words in the existing content name and the search term set is an exact match. This is proposed 1. Next is the processing node doesn't know the existing content name. This is proposed 2. Proposed 1 mainly implements three components. First, acquires an existing content name from the neighborhood node. Second, scans the existing content name that matches the search term set. Last, it sends out an interested packet using the matched content name. In this method, the generated content name interest packet is fixed at 1. But since the content name is also acquired from neighborhood node using Cefore, two sessions are generated. We also described a method of acquiring existing content name from neighborhood node. Basically, we are thinking of using FIB. To output the FIB, the status management command of the for is used as the simplest method, and the existing content name is extracted from the status information of the FIB obtained as the standard output. These contents are stored as contents in the CS on each content router. In addition, a uniform content name is assigned to the content that has existing content name. This makes it possible for the system user to retrieve the content that has existing content name regardless of where the user accesses the CCN network from. There are two components to be implemented in proposed 2. First, generated all possible content names based on the search term set. And next, it sends all the generated content name interest packet in parallel. The number of candidate content names in proposed 2 dependent only on the size of search term set. And if the size of the search term set is n, then the number of candidate content name is determined by the mathematical expression shown in the slide. The reason for the parallel delivery is the specification of the Cepheus file command of the Cefore interested delivery command uses this report. This Cepheus file command is implemented as a sequential processing command, and this the time required to process multiple interest packets, increasing linearly with the time required to send an interest packet only once. Therefore, we try to reduce the processing time by implementing parallel delivery. To implement parallel delivery, we use the multiple library in Python and execute the Cepheus file command in parallel. In the specification of Cefore, the maximum parallelism is 15 when the multiprocess library is used. Therefore, if there are more than 15 content names interest packet to be generated, the implementation involves multiple parallel executions. Next, we evaluate the implementation described in the previous section. The purpose of the evaluation is to measure how much difference there is between existing method and implementation method. The existing method here refers to the system user knowing the content name of the content and using the Cepheus file command to process the content. We evaluate the implementation as good as possible if there is no difference in performance with existing methods. The environment for the evaluation experiments is shown in the figure slide. These two nodes shown in the figure are wired together via Shon switch. Uh, User node 1 is treated as a user node and node 2 is treated as a producer node and content router. In addition, the parameters required to perform the experiment are summarized in the table. We specify the size of the such word set as input with 325, the number of trials as 100, and the size of the data packets as 144 kilobytes. First, we show the processing time result of the existing methods. The average execution time was about 2 seconds. In order to see the variation of processing time, we prepared a graph with the difference between the average execution time and the number of measurements on the horizontal axis and the vertical axis. It can be seen from the figure that the existing method follows a normal distribution around the average execution time. In the next section, we show the result for proposed one. The average execution time is around 3.9 seconds, which is more scattered than the existing method but follows a normal distribution. Finally, we show the result for proposed 2. The average execution time is 2.6 to 7 seconds. This is because request processing is performed multiple times when the number of generated content name exceeds 15. Looking at the graph, we can see that it follows a normal distribution. Expect when the search word set is 5. From the above, it can be concluded that the proposed method has a certain stability as well as the existing method. Finally, the average processing time for the experimental result is summarized in the table slide. Among them, when the number of elements of the search term set in proposed to is 5, the execution time is long. We also consider the change in processing time when the number of elements in the search term set is increased. First of all, considering the processing time of parallel processing 15, in the case of the set of such word with 5 elements, uh, parallel processing 15 needs to be executed 3 times. But compared to the case with 4 of 4 elements, it can be seen that it takes about 2 seconds to execute parallel processing 15. Based on this, if the number of elements in the such term set is 6, the number of generated content name in proposed to is 720, which means that 15 processes with 50 parallelism are required. The total processing time is expected to increase linearly if the processing is performed without any problems when the processing is performed at 15 degrees of parallelism. Therefore, it is expected that the whole process will be completed in 30 seconds or so. However, the average execution time of 29 seconds was obtained under the same conditions as in the evaluation experiment. Tenth, without considering the particularity of this processing time, we can assume that the change in processing time depended on linear increase in the number of elements in the such sum set. Finally, this presentation is summarized. The purpose of this research is to propose a flat naming scheme for ICN, CCN, and we have explained the algorithm and implement method for the scheme. Algorithm, we have not been able to develop a comprehensive implementation of the proposed algorithm. We have proposed a simple implementation under restrictive conditions and evaluated the effectiveness of the proposed method with experimental result. Our future work is to build a system that covers the algorithm of the proposed method and to implement it. In addition, it is necessary to define more practical evaluation experiments using this system in the future.